Hello, everyone. So this week we have Benoit and Jordan from Zama who are going to be telling us about privacy-preserving ML with fully homomorphic encryption.
Hello, everyone, and thanks a lot for the invitation. So to Thomas and to Peter, who helped us being there. It's great to be here to have the possibility to speak with you. So we are Zama, which is an open source company in France, working on the fully homomorphic encryption. So we are going to remind you what it is about. But mainly what we are doing in the company is building tools for developers, thanks to TFHE, so that they can add privacy to their application without really needing to understand how it works under the hood. And we are in the US for RSA first. We had a presentation there, and also we use the occasion to meet a few companies and discuss with researchers. So if you think about HTTPS and you have a client and a server, you have the data on the client side, which may be very private, and on the server side you have a function F that you want to evaluate. And when you are going to do that, you are going to encrypt the data during the transport. But once it's on the server side, everything is decrypted. The computation is done in the clear. So the server knows X and F of X. And only when it's back to the client, it's only encrypted during the transport. So as you can imagine, it's secure against eavesdroppers. But it's not secure against, a curious server or security breaches, which may happen on the server. So we all know that there were a few bad security breaches. For example, 23andMe, where millions of DNA records are in the wild because there was a security breach. So with TFHE, fully homomorphic encryption, we want to avoid this. So the principle is a bit different here. We are going to encrypt X on the client side with a key which is only known to the client. We are going to send this to the server, and then everything which happens on the server side is encrypted. The key is not on the server side, so the server will never be able to decrypt anything. But still, thanks to some mathematical properties of fully homomorphic encryption, it is possible to evaluate the function f, or actually a function which is very close to the original function, and with public key material. And at the end, you will get a result which is an encryption of f of x. You send it back to the client, and the client with the secret key can get the f of x in the clear. I didn't mention, but if ever you have questions during the talk, you don't hesitate to interrupt us, and we can answer. Okay. So TFHE, the principle was invented like 40 years ago. But for years, we or the cryptographers haven't been able to find a practical solution to this. It's only 15 years that Gentry has shown a first implementation, but still it wasn't practical. But then in the recent years, we have seen a few improvements, new schemes, and now things become practical, and companies like Zama are created to build on top of this. And so amongst those crypto schemes, there is one which is called TFHE for Taurus Fully Homomorphic Encryption, which is the one that we are using here at Zama. So this is not a crypto talk, so I'm not going to speak too much about the internals, even if you have questions, we can try to speak about it a bit. But just from a user point of view, what can you do with TFHE? So the first thing is it's pretty simple, but you can add ciphertext together. You can multiply a ciphertext by an integer. And one thing which I didn't mention is that computation in TFHE are done on integers, not on floats. So we'll see how we can handle this in the machine learning side with quantization. So the first two operators are very classical in the TFHE world. The third operator is about what we call the bootstrapping. So here, it's just a bit of crypto. So in crypto, when you have TFHE, more or less you have a noise, which is important for the security, and the noise grows when you make more and more operation. So basically, the idea of the bootstrapping is to be able to reduce the noise. So you have the same plain text, the same clear value, let's say, but the noise is reduced such that you can continue the operations. And then the fourth operator is very important for us, and it is actually the reason we have chosen to use TFHE. So that's the availability of a table lookup operator. So here, at the compilation time, you decide the table T, and you can apply the table T over an encrypted data and directly get T of X. So here you can see that this is the only nonlinear operation, and this is our way to replace nonlinearities in machine learning models or in other kind of computation. And this is really the operator, the reason why we have chosen TFHE. In the other main TFHE scheme, they don't have the table lookup operator, so they have to replace it by approximation with polynomials, but then it's approximation and there are a few issues with that. So table lookup is great, but this is the expensive operator in TFHE, so we will try to avoid to use too many of them. Or we will also try to reduce the size of X, so the input of the table, because actually when X is larger, the table lookup, which is called the programmable bootstrapping, PBS, in the encrypted world, is slower. That was the question. Also, I didn't see the question. Go ahead.
Yeah, sorry to interrupt. So there's no multiplication here of...
Exactly. Okay, so excellent question. So we have a multiplication by a scalar, but you're right that we don't have, let's say natively, the multiplication of two ciphertexts, which is different with CKKS. So I told you CKKS is the other main TFHE scheme, practical one. And in CKKS, they have a native multiplication of ciphertext. So that's, let's say, a disadvantage of TFHE. In TFHE, you can reproduce that, but with table lookups. So you have more or less to apply two table lookups to have the equivalent of ciphertext multiplication. And we are going to see later in the LLM part, the large language part, that it will be one of the bottlenecks. But so it is possible, but it's slower than with other scheme.
Thank you.
Hi? Okay, great. So yeah, we wanted to show you this in practice. So on Hugging Face, we have a few demos and also a few blog posts about concrete ML and how to use TFHE with machine learning. So this is the demos that we have made to show how to use TFHE in practice, and I wanted to show you one of them. So here it's about image filtering. If it loads, yes. So the idea is that you have some image on the device, which might be an Android phone, and then you are going to encrypt the image, send it to a server. So the server will not see the image is, let's say, random looking, but still, thanks to TFHE, the server will be able to apply a function. So here, some kind of filter. The result will also be random looking. It's still a ciphertext. And then you send it back to the client, which with its private key is able to decrypt and finally get the result. And so it's something like this. So I could have done it with the Google logo. Sorry, I haven't it there. But so you select an image, you select some filter. So you generate the key which stays on the device. You really don't want to share it. So you are going to encrypt the image on the device. You send it, so it's random looking. You send this to the server, and then once you are on the server side, you can make any TFHE computation. So here it's very simple. It's just an application of some convolution to apply the filter, but we could do things which are a bit more complicated. And then you send it back to the client. So this is just to show you that more or less what the server sees is nothing. And then you can decrypt and you will have the right, it's the application of the filter, the original image. So we have a few other demos on the Hugging Face page if you want to have a look. And also we have more examples on the repository. That you can also reproduce. We are a bit limited on Hugging Face because their servers are not very powerful. I mean, it's not made for that. So how does it work? What was our question? Oh no.
Right. There's another question. So for black and white, you can get there with like scalar multiplications, right, of each pixel. Is this like treated as like a scalar, like a public scalar in your FHE?
So here it's I think it's
you mean it's plain text, right? It is.
Yeah,
So the multiplication, it's a ciphertext with a scalar, and scalar is in plain text.
Yes.
Okay.
So it's the application of a convolution, and the convolution is not encrypted. So that's the fast case.
Mm-hmm.
Okay. So it was the beginning was very easy. Let's try to go a bit into the details. How does it work? So I told you the different operators which are available in TFHE. So what we are doing in the different products is that we are replacing the functions that you know by operators which exist in TFHE. And basically at the end, you will have something like this. So you will take your machine learning model, trees, deep learning, whatever. And then for linear operators, like a dense layer or convolutions, fine, it's easy to do with TFHE because additions are native. And then for the other ones, like activation or max, same thing, max is non-linear. We are going to replace them by some calls to table lookups, which are the PBS in the encrypted world. Okay.
How big of the lookup tables for the typical implementation?
So you'll see that it really depends on the use case. So we can deal up to 16 bits of integers, but when you are at 16 bits, you are not happy. So we try. You would see that we would use that most of the time to like 6 bits, and by still maintaining the accuracy. But you'll see that. Okay. Now the talk to Jordan.
Yes, so now we're gonna dive a bit into the machine learning models that we convert from the plain text model to the FHE world. And we will start with linear models. So something that Bruno mentioned is that in our FHE world, everything has to work on integers, right? Inputs, outputs, intermediate values, parameters of the models, everything. So we need a way to pass from the floating points to the integers. And we are lucky because it's the time everyone wants to quantize their model. So we are going to use quantization, right? So we developed a tool which is called confidentiality that does everything behind the scenes. We're going to present that right after. But in this tool, you can train your models. So here it's linear models. You can train it using any kind of solver you like on clear text, on clear data. Or you can actually, we recently released a way to do encrypted training. So the data are encrypted and you use stochastic gradient descent to make the model converge and train, actually learn the weights, right? So you have two ways to do this. We're going to come back to the encrypted training data. And very importantly is how we actually pass from floating points to integers. And this is fairly easy. The main approach that everybody is using is this quantization. So it can be asymmetric or symmetric quantization. It's not very important. It's basically whether you want the data to be centered in zero or you. Basically, asymmetric quantization allows you more precision, but it makes the operation in the integer world a bit more complicated. So the way we do this is simply a linear transformation. So we take the floating points x and we scale this up. So mainly it's up because in the floating point world, it's going to be between -1 and 1, for example. And you want this to scale between something like 0 to 255, right? Such that you maximize the 8 bits precision, for example, right? So what we do is this, we scale up and then we round. So we round to just discard all the decimal values. And then we have the 0 point to just be sure we are in the right range. So we do this on the inputs. We do this on the intermediate values, so activations inputs, and also all the parameters, right? So now we have different scales, different 0 points for all our tensors. So we have to implement operations like general matrix replications, convolutions, such that the integers correspond to the floating points operations. And at the end, what we want to do is to decrypt and then dequantize. So go back from the integer world to the floating point world, right? So linear models, they are fairly fast because, there is not this programmable bootstrapping that Benoit talked about. So it's in the order of 10 to 100 milliseconds per example. We are in the TFHE world and we talk about performance over a single example here, right? And something that is good is that 8-bit quantizations works for most of the use cases. You can go higher than that for linear models, but we'll see that later. We want to remain around that 8-bit quantization as for inputs and weights, right? On the right, it's just to give you an idea of how this in practice impacts the decision boundaries. You can see that there are little steps within the decision boundary. And then outside the boundaries, it's basically, you shouldn't go there, actually. TFHE has a kind of acyclic behavior where you don't want to actually go. So you want to remain within the boundaries. But that's good because in machine learning, we do some assumption that distribution of the test is going to be the same as the training. So fair enough. Great. So now we dive in a bit more complicated stuff with the neural networks. And from the high-level point of view, how we actually manage transforming any kind of model into the TFHE equivalent is by representing the model. So on the right, you have an ONNX representation of a machine learning model. What you can see is that you have some convolutions, some ReLU, some max pooling. And every single part of this model is actually either linear, so it's going to be the fast part of the TFHE, or it's non-linear, and then we can build it with table lookers. Right? And this is basically what we do in CompleteML. We take the model in ONNX and we convert everything to either linear parts or table lookers. And now comes the very important part. So this is just a very simple representation, a neuron, right? You have some inputs, X, and some parameters, Y. How we actually work on this is naively quantize the inputs, and I really quantize the weights using p bits. So, for example, 8 bits. What is going to happen? The first operation is just multiply the x with the y's. So if you have 8 bits in both, then you end up with 16 bits, theoretically. But then there is another thing which is the accumulation, right? So you have multiplied the inputs with the weights, and now you need to accumulate. So this equation, which is completely messed up, is basically just y equal the sum of the w I xi. And this intermediate value, which is the accumulator, is the one we don't want to be very high, because what's coming next is the nonlinear activation. It's our table lookup, and we don't want this to be 20 bits, for example. We don't want table lookup with 20 bits of precision, right? So there are a few ways we can work on this, but it's very important to see how we are slightly different from the state of the art in the literature in quantization. We quantize the inputs, very important. They don't often do it in the literature because they are mostly interested in about minimizing the memory usage of the GPUs, for example. And the second part is that actually we don't really care about the precision of these inputs and weights. What we really care is the accumulator, the intermediate value right before we apply the execution function. Right, so how we can actually make this y smaller? Well, the first way to do this is use lower quantization precision, right, on the weight and the inputs. Well, it's easily said, but if you use very low precision, then the accuracy is going to drop because you're losing a lot of information. So one thing that people use a lot is quantization-aware training, where you can achieve this either by training from scratch, or you have a pre-trained model and you want to fine-tune it for a few iterations. And the most important thing here is that at inference time, you're going to quantize the model. So a prediction of the model is going to have the error coming from quantization, right? So when you backpropagate, you're going to correct this quantization error. So you don't need to actually do a lot of iteration, just a few to correct all the quantization artifacts that will make the accuracy drop. And this is what people use for a few iteration, even on LLMs, to go very low in the number of bits you use for precision. So there are a few things about how you can actually use this. Since there is the rounding operator here, you can actually compute, you cannot compute the gradients. So there are some tricks like the straight-through estimator where you just make the gradient go through this backward pass for the rounding. But it works pretty well. So you can make the model converge and just catch up on the loss that the quantization made to the model. So we have built-in neural nets. So here is just a very simple, again, example where we have a 3-layer multi-layer perception with Frery activation. We use 2 bits for the weights and 4 bits for the inputs and the activations. And we end up with 6 bits for the accumulator. So as you can see, the decision boundaries, you can see even more that is stepwise. This is due to the fact that we are almost at the maximum, at the lowest precision we can go for the weights. It's 2 bits and only 4 bits for the inputs. So it's very low, right? And actually, even going that low, we still need 6 bits. So 6 bits is not a lot, right? And you're going to see that we're going to use 6 bits in the accumulator for most of the models. We found that to work pretty well for a lot of different machine learning models. But it might not be enough in the sense that, well, if your neural net has thousands of connections to the neuron, even though you go to 1 bit of precision, you might not reach the desired accumulator. So we don't really control it as we would like to. So we'll see later that we're going to have a way in FHE to achieve that. So this is an example just to show so basically I showed you the naive way, which is the post-training quantization. You take the pre-trained model, you apply quantization, and that's it. And the other way is the quantization aware training. And here, so on the left graph, for example, it's MNIST with a fully connected neural network. The numbers on the graph are the accumulator bit width, and on the x-axis, it's the weights and activation bits. And as you can see, starting at 2, 3, 4 bits of precision, you are going to have a lot of loss in the final model accuracy, right? While the quantization aware training is just very, very much, very quickly catching up on the loss. And you end up with relatively decent accumulators, right? And the same goes for the CNN. Here it's a small CNN as well. And you can see that quantization aware training helps a lot. Yes.
For the quantization aware training, do you start from the non-quantized thing and then more training, or do you train from scratch?
Yeah, so 2 ways of doing this. The better way, when you have a very large model, is just to fine-tune. You don't want to train from scratch. Nobody wants to retrain 7 billion parameters. So, so what people do is just take the model as it is, pre-trained, and do some quantization. And at the beginning, they don't even quantize everything. They start by quantizing the last layers, and then they quantize with 16 bits, and then they go lower. So there are some steps to achieve the optimal precision.
Makes sense.
So people currently are able to quantize LLMs with 4 bits of precision and keep accuracy stable. It seems to be much harder to go lower. And we'll see that 4 bits is still a lot for the accumulator. So we need a solution. And as I said, the most important thing here is the accumulator. We don't really care about the weights and the activations, in fact, because we can do the matrix multiplications, have a high accumulator. What we cannot do is have this high accumulator in the table lookup. So what we are doing is to actually just replace this table lookup. So imagine you have a value I over 20 bits, it's the accumulator, and you have to apply a table lookup on this. What we are going to do is build a T prime table lookup on I prime, where I prime is just the most significant bits from I. Right? So in FHE, we have an operation that can allow us to discard the least significant bits. So from the 20 bits, we just discard as many as we want, and we end up with something that will be very fast. And it turns out, like, most machine learning models can work very well without the 20 bits. They don't really need that. It's just an artifact that comes from the architecture of neural nets today. Because you have this big accumulation, you end up with very large precision, but it's actually not necessary to achieve decent accuracy. And this is basically what we see also with the weights. We don't really need 32 bits floating points. It was needed for training maybe, but at inference time, it's way too much precision. We don't need that. And it's even worse for the accumulator. Those giant precision are not necessary. So we can just cut them without any fine-tuning, and it works pretty well. And we can do this for free in FHE and end up with very small table look, right? And finally, the last acceleration that we have here is playing with the by one error, which is a probability of that the result of the programmable bootstrapping is off by 1, right? So we set this to be super low. It's something like 2 to the power of minus 40. But if you want to, if the machine learning model is resilient enough to achieve similar accuracy with more error, then it will boost the inference in FHE, right? So that's the second way. I think. Oh yeah. So we have a table with a small example that we are keeping in our repository updated, just to show how FHE is evolving. So we started with just building a VGG network. So it's 9 layers correlation neural net on Cypher, which are 32 by 32 images, color images. So we trained it, right, using quantization over training, 2 bits for the weights, 2 bits for the activations, and 8 bits for the inputs. We need more precision for the inputs. We achieved like 88.7 accuracy in Torch. And the first thing that we had to do is benchmark this in FHE. So we had a way to actually do the simulation. So it's a very fast inference, as fast as in clear, but it reproduces the same outputs as the FHE. So we can actually see with all the rounding, with all the error probability, if the accuracy remains stable. So this is the first thing that we did without rounding, the trick I just presented before, and we got the same accuracy. And then we start using rounding. So we started at 8 bits and see how this impacts the accuracy, and we go lower until we reach an accuracy that is good for us. So that will depend on the use case. And finally, once we are happy, just a note here, 6 bits table lookup are currently the best we found to go very fast and maintain accuracy. Going lower would imply having a bit more work done on the model. So once we are happy with that, we just went for the full FHE inference over 100 of examples and checked that the accuracy is exactly the same, and we did so. That's where we are for this model, and Benoit is going to show a bit of how performance was by these encryptions.
Yes, the goal of this rounding property was to have things which are faster. So this is what is shown in the last slide. So here it's small, sorry. So it's execution time we have seen for this cipher in the last 2 years. So
maybe one thing, I presented like around 2022 in the Google Tech, and we were around that.
Exactly. So when we started like 2 years ago, we already had this VGG, and we started at like 40 hours per inference. So it was huge. So not sure we mentioned the execution time when we presented the first time. And now, so we've made a lot of improvements, and now we are at 40 seconds per inference in 2 years. And it comes from the different levels of the stack. So first, the machines. The machines are better. Each time we try to use the best machine which is available. So that's a free optimization. And then there is a cryptography optimization. Things are faster with the crypto. There are optimization also in the compiler. So we are going just to mention it a bit later, but under the hood, there is a compiler that we use and an optimizer which tries to find the best crypto parameters. So we have had improvements there. And finally, there are improvements on the machine learning side. So for example, this huge improvement that we've seen before with the rounding was really important for us. And so today we are at 40 seconds. It's not the end. We expect it to be smaller. Not sure we will have the same gains that we have seen in the last 2 years, but not sure. And also we are starting to work with GPU. So for now, it's really the first experiments. There is nothing even public. So it's just internal. But we are at like 28 seconds per inference. So without much work for now. So here we will see a lot of improvements. So when you hear that TFHE is slow, I mean, certainly it used to be slow and it's more and more practical. For linear models that we have mentioned, it's very fast. For trees that I'm going to explain, it is very fast. For deep learning, here it depends on the kind of models that you have. Yeah, certainly you can't be real time, but we are not too far. And later we will have the we will have the hardware accelerators to make it even faster with GPU. I've mentioned with the FPGA, and later with ASICs. So trees. But if ever you have questions about deep learning, don't hesitate. For trees, so we have explained the linear and deep learning models. It was almost the same kind of techniques. For trees, it's a bit different. In trees, you have branches, and branches are not compatible with TFHE. So when you look at this first, you have the impression that it will not be able to make trees in TFHE. Fortunately, it is possible to do that. And for this, we've used the technique which was developed by Microsoft, which is called Hummingbird. So in their case, they were using this technique for vectorization. So they do all the computation at the same time. For us, it will be the same kind of thing, not for the same reason. So I'm not going to explain everything in detail, but just I'm going to mention more or less how it works. So you start with the inputs. You are going to have a dense layer just to select the inputs in the different conditions. So here it's just a matter of, let's say, moving things. So you will have a value, and then you will compare these values with threshold. So you know the integers that you see in the larger conditions on the dot. So here it's a PBS to programmable bootstrapping to make these conditions. So you will have booleans. And then you will have a second dense layer to more or less add the conditions together. So you will add the conditions which are supposed to be true and subtract the conditions which are supposed to be false. And then you will compare these numbers with the expected max number for each of the branches. So only one of those max will be reached. So what you will have after the second level of PBS will be a one hot vector with a 1 in the branch that you are in. And finally, you will multiply this one hot vector by the vector of the expected outputs. And that's your way to select the right output. And so if you look at this from an higher point of view, more or less, you can see that it's really like an MLP with two layers. So two layers of activation, and that's it. Actually, in your MLP, there will be a lot of zeros, but more or less the structure is the same. And it works very well. So we've mentioned that linear models are in the tens of milliseconds. For trees, typically, it's like in 200 milliseconds. It depends on your parameters, but that's also quite doable into production. So we will give later the links to the papers if you want to have a look to the precise details. But here, just some graphics to show you that same thing, you have to quantize this in trees. And here we show that the baseline is for floats. And what we show is that obviously if you quantize too much, your accuracy is bad. But as soon as you have like 5-6 bits, you are very close to the accuracy in the floats. So that's sufficient. And on the right, you see it's also a bit expected that if you have more quantization, the PBS are going to be with larger input. So obviously things are going to be slower. So you see the matter of trade-off to find the right parameter. So obviously, most of the time it's between 5 and 6. So here it's some examples where you see the difference between decision tree, XGBoost, and random forest, and you see the difference between TFHE, so on integers, and their float counterparts. And more or less, you can see that the accuracy is very close, and that the cost is like 1,000 or the cost of TFHE. So all of this is the techniques that we have to explain in the paper and so on, but no one wants to do that by hand. So we've done a product for it. So this is just a few slides to explain how how the product is and how we use it. So this is the stack that we are using. So Concrete ML is what we have mentioned. So it's the equivalent of scikit-learn and Torch, but over encrypted data. And all of this is based on Concrete. So Concrete is our compiler. So it's a compiler. So more or less, the body of the compiler is based on MLIR. And then you have a front end. So for now, we just have a single front end, which is a Bison front end. But we could imagine that Zama or some other parties add some other front ends to support different languages. And then same thing for now, we are mainly on CPU backend. We start with GPU backend, but when we will have hardware accelerators or FPGAs, we will add more and more backends. And then in terms of usage, so really one of the goals of the company and one of my goals personally was to make that all of this is easy to use for people and especially for non-cryptographers. So our target users are data scientists, machine learning people. They are not cryptographers. So we have tried to expose things which are familiar to those people. So here you have the example of logistic regression. So instead of importing from scikit-learn, you would import from ConcreteML scikit-learn. And then same kind of API with just the exceptions that you need to, it's better if you give the number of bits of the quantization. They are default, but if you choose, it's better. And then you fit and predict as you would normally. And when you are ready with the hyperparameters, you can compile, which means that the model will be turned into its TFHE equivalent. And then you can predict either in simulation, which will give you the same kind of accuracies and in TFHE, but in a much faster way. So that's a way for you to check your hyperparameters, maybe grid search or that kind of things. And then when you are ready, you can go in production with TFHE. And same thing for trees. Trees, it's really like in scikit-learn. And then for deep learning, so here we have you can do quantization while training if you want, or you can apply post-training quantization. So this is our preferred solution today, and also it's easier for users. So here we have shown that you can go to Hugging Face or to wherever you want. You download your models, and then you will compile them. And there will be some kind of post-training quantization with a rounding and so on. And then you will be able to make your forward in TFHE. So most of the things that we have explained for now were related to the inference, but we are not restricted to this. And we have started to work on training. So here we have like two flavors. So what you have on the left is we are compatible with other private training. So if you are using federated learning, if ever you are using differential privacy or anything, you can train with your techniques. And then once your model is trained, you can import the model into ConcreteML. And then we will offer like the TFHE predictions for them. So in the repository, you have an example with Flower, and it works pretty well, but it would work virtually with a lot of other techniques. And then on the right side, we are working on TFHE training. So here we are directly with the data set that we get is encrypted in TFHE, and we are making the training directly in TFHE. So for now, we support linear model training and a small ML piece, and we will continue there to add more and more.
So on the right side, you said the model is also encrypted.
A great question. So as your data set is encrypted, what you are going to have at the end of the TFHE computation is something which is encrypted. So your weights are going to be encrypted. Then for now, what we propose is that you decrypt, the owner of the model, the owner of the data, because the data are encrypted with some key. So the one who has this key decrypts the model, and then you can have the predictions in TFHE. It might be possible to keep the model encrypted, but then we would have to deal with keys. That would be the keys of the model, so of the weight, and the keys of the user when they make the queries. And TFHE is already quite complicated. So if you try to do TFHE with several keys, it's even more complicated.
So the second line said the encrypted model are trained on encrypted data. So I wonder, like you said, right now the schema is using our encrypted data with scalar. That's the multiplication is okay. But in this scenario, isn't that like too encrypted?
So yes, you're right that when you train in TFHE, there will be dense layers between encrypted matrices and encrypted vectors. Is it your question?
Yeah, I wonder like how multiplication or
so you can do multiplication between ciphertext. So if I can write on the
Yeah, computer.
okay. Okay. So I will just read it for the people. So actually, xy is 1/4 of x plus y u squared minus 1/4 of x minus y to squared. And what you can do is that you can compute z1, which is x plus y. It's an addition. Z2, which is x minus 1. And then you have a table lookup of TFHE, which is 1/4 of I. That's what. So as you can see, it's the application of two table lookups.
okay.
And you will have the x1. Yes. And so it's not as fast as it would be with CKGS, but it works. And there is no scheme which is perfect. For us, we wanted to have a TFHE because we have this table lookup operator. On their side, when they have to replace activations, it's complicated for them. Okay.
To give you an idea, we can train linear models with stochastic gradient descent and per batch, which are like 64 example. It runs in around 10 seconds. So 10 seconds, one iteration. So example we have, but it's in the order of the hour to train a model.
Yes, sir. Thank you. And then, so larger language models. So this is what we have spoken about at ours.
Yeah. So this is just an extract of what we are talking about, but this is just to give you an idea where we are. And first, I would like to say we're not going to run end-to-end large language models today. And this is mainly because of one operation that is within those kind of models. So if we just look at how those models are executed, what operation ran in there. So we have the linear parts, right? So embedding and linear parts, which are the very simple and super fast part to execute in TFHE. Then we have the nonlinear activations, which are located in the MLP part of this transformer block. So everyone uses GeoLib for some reason today. And so this is also quite fast in TFHE. And now comes the funny one, which is also the one that makes transformers work better when they scale up. It's the attention part. And in this part, we have the softmax. But for us, the bottleneck is really, we are going to have encrypted matrix multiplications in there because the attention, how it works, it basically projects the input into 3 different tensors all of these tensors are encrypted for us, right? They all come from the same input. And then you're going to have to multiply them together. And in scale quadratically with the number of tokens that is in the input of the model. So you can actually see how what's the problem here. That we are going to have to do this trick that just Benoit wrote on the board 2 times per every single multiplication. So it's costly. It is very costly. So all the first parts can run in millisecond. The softmax is a bit more complicated because it's a division. So it's basically encrypted multiplication again. But they are not a lot, so that's okay. The last part is just basically what is pretty hard. And it's minutes, hours, depending on how number of tokens you have in the inputs. Right? So we had to find a way to still work with LLM, but dodge this problem. And we looked at actually where is the IP located, or where is where is the IP located, or where are the weights actually located? Well, it turns out everything is in the linear models, in the linear parts. So the embedding and the linear parts have all the parameters of the model. There is nothing in the attention. Projection that we do are just linear operations, right? So if we look at it like this, what we can think is actually doing only the linear parts on the server, on the third-party server. What this allows us to do is to outsource all the memory problem that currently are. So currently LLMs, it's a mess to run locally because, 70 billions of parameters is a lot. And it's not looking like people are making this small. So it's going to increase, and you have to fit this on GPUs. It's a problem, right? So what we can do is just take all the parameters, put them on a third-party server, and the client is going to ask for the linear parts in TFHE. So what happens is that on the client side, you do the tokenizations, text to integers, right? Then you can encrypt that and send everything to the server, which will run the embedding, the QKV projections, which comes right before the action. And then this is sent back to the client where it's decrypted. The attention is not that costly to run for the client because it's all in clear. There is not huge problem here. And there is 0 parameters to mount in the RAM, right? So no problem of memory. And attention is applied, and then you can go do the whole thing again as many times as you want. Great. So this was a quick summary of how we're actually using the TFHE on the LLMs. We have a few work in progress. I'm going to go quickly because we're reaching the end. But basically, we do some kind of secure anonymization, for example. So right before you send the text to ChatGPT, for example, you are going to ask for de-identification. This can be a bit of a problem if you want to use an external party. So what you want to do is use a machine learning model on a third-party server, but you're going to encrypt the text, send the text encrypted to a third-party server, which will say which words needs to be de-identified. And then this goes back to the client. It's decrypted. You only have IDs in there, and you can send this to any kind of LLM you want. And yeah, the LLM works with IDs. They can do this pretty easily, and then it comes back and just go from IDs to words. And we have actually a team who on that. Another work in progress is collaborative computation. So when you have several parties, like several companies, for example, that want to give features to do an inference on a model, but they don't want to share the value of those features, you can do this using public key TFHE. It just encrypts all the features with the public key, concatenate all the features, run the model on these features, and you can decrypt using threshold decryption, which is an MPC protocol. And lastly, it's a data frame. So this is very starting. We can basically merge TFHE encrypted data with clear data and do some operation as we do with that other static frame. Great.
Yeah. So yeah, something I'm going to be very quick. So we are open source. We've said it. So if you want to have a look, you can have a look to Concrete and Concrete ML repository and see how it works under the hood. The documentation are pretty extended. So you should find your information there. But if you can't, we also have the support in it's called the TFHE.org. So here you can ask the developers. So we are there, but you can also discuss with the other users and also all the other TFHE companies. There are a few papers which were written to explain what we have described here. So the first one for the training, another one for the deep learning part, and the third one for the trees. So if you want to look at them, there are more information there. And then I hope that you will have been convinced that you should give it a try. So if you want, you better to start by reproducing the examples, then start small. Don't try to already, start with an LLM or some huge model. It will not work. So start with something simple like machine learning, so scikit-learn. And then when you are familiar with it, you can try with deep learning. So with deep learning, maybe you will have the issues with the quantization, with the too large accumulator. So you will learn how to round things and make things more efficient. And that's it for us. So thanks a lot for your time. And once again, thanks a lot, Thomas, for the presentation and the organization.